And the difference between this one and the normal capacitor is they have something connected to the two canals, right? So like I say, if I charge the positive, negative, and now you have a potential difference of U, by connecting them, you're actually discharging. So you are going to see a current going down, right? Okay. And they are saying something very fast or very small, something like that. So they are saying that the momentary voltage is U, etc. So why is it momentary? Because this thing is going to change, right? You're discharging, so this voltage is going to drop. At this moment, when I see it is U, and I have the distance, I have the radius, is the wrong thing. And I want to ask you a few questions. And what else? They also give you the current, that is I. The first one is what is the angular flux density? What is the pointing vector? Pointing vector. Okay, you're going to see this value again and again in this curriculum, in the latter chapters 2, and in the exam. Definitely you're going to test it is the favorite question, pointing. And so you need to know what is pointing vector? E cross H. E cross H, right? So what is E and H used? In this case, we have they give you U already. So that means there is the electrical field, right? I have a little difference. I have a U. Where I have a U, I have a current means I have a electrical field, E. So you got the strength E. Another thing is, this current here is going to give you a magnetic field. Magnetic field. Remember Ampere's law. This is why they give you the current, because Ampere's law requires the current. Ampere's law is saying the integration, the loop integration of H will equals to the I. This is why they give you I. Okay. Without looking into the detail, this is my understanding of this question. So now let's go through the part A very quickly. It's quite straightforward actually. So I believe you all have this page. Remember, our final target is we're going to have S rank. What is this value? And this value equals to E cross H. Okay. So I'm going to find my E and H. And I do not have E, but I have U. And I do know the potential is the integration of E, right? U is the integration of E. Oh, actually, in most of the simple cases, I mean, when they say the thing is fixed, they say that they don't say the field is changing. If they don't say the field is changing, you can use something simple. That means if I have a capacitor and with the U and with the distance of D, the E, you can always use U divided by D. Okay. Unless they say the thing is good. Normally, you can use U over D. For most of cases of at least the parallel capacity. Huh? Repeat what? From the beginning of the class. Come guys. Yeah. What do you the U of D. So whenever you see two parallel panels, okay, a capacitor, you see a capacitor, and they are saying there is some potential, and they don't mention this in change. You don't think this thing will change. Like this one, I told you it is going to change because you are discharging. However, they say momentary. For now, for any moment it is static, right? Everything in motion at the moment is static. So this thing is static. So you think parallel, static, you can use U over D. But of course, the safer way follow integration. Safer way is follow integration. And if you really want to follow integration, this is, they say, if you integrate the E on this loop of the current, means from top to bottom, you integrate. You think this way, if momentary means E is static, right? E is a constant. So that means you can bring the E out, become something like this. So this integration thing actually is E times integration of what ds. Okay? Right? Because E is the constant, we're supposed. And ds, S is the loop of my integration, means roughly S is from here to here. Okay? This is my ds, but I need to all the way go up from down. If you integrate on this linear component, you get the total distance D. So that is to say integration this part equals to D. Okay, so E will equals to U over D. However, I have to say this one is only, this is my shortcut. I hate those things. I hate those calculations that include everything. We're always trying to calculate everything in one equation. So that means the calculation is very, very complicated. I always separate the magnitude with the direction. So in this case, the E over D is the magnitude, but it still have the direction because E is the vector. Okay? U is the scalar, D is the scalar. So this guy is the scalar, meaning the direction. Direction, you just think, what is the direction? If the current is going down, U is going down, the E is also going down. So how do you denote something going down? Eventually, you need to choose a coordinate system. In this case, I gave you the plane, I gave you this cylindrical thing. Let's use cylindrical system. So something going down in the cylindrical system, we use negative Z. That is negative Z, right? Something going down in the cylindrical system, that is negative Z. So this is how what this part is. So I have a magnitude and I have direction. Okay. So the first part is done. I have that. Okay. Okay, next one is my favorite, Ampere's law. Ampere's law is saying, remember, after finding E, we're supposed to find the H. Ampere's law is saying if you integrate H on the loops, what is the loop? The loop is where the magnetic field goes to. The way it goes to. Integrate H on the loop, you have the current. And now I give you this current. So you need to find out what is the loop. So in this case, there is current going down. Firstly, right-hand rule. For the current going down, this is the loop, right? Imagine your forefinger is surrounding. This is a loop. And this is the direction. This direction is something like if you look from the up, it will be clockwise. Okay? Clockwise if you look from top. Okay? So that direction in a cylindrical system, what do we call that? Cylindrical system we have three things. One is R, one is phi, one is Z. That actually is phi because it's something rotational, right? So it's positive or negative phi? Something like this. Is that positive or negative phi? This is negative phi because positive phi is going counterclockwise. So this is definitely negative phi. So this is why I have this one. Okay? I know this way, this field got this direction of negative phi, of course. Something like this. Okay, and then in that case, the same thing. Now we have finished considering the direction. Let's go to the magnitude. We talk about the magnitude of the H. And let's just say on this cylindrical surface, everywhere you add the same distance with the center. That means your H will have the same value everywhere. Magnitude will be the same. So again, H is the constant. If you move H out, you are integrating the ds on this circle, so you have the total distance, that is the circumference. Okay, remember, you integrate on the one line, you have the distance. Integrate on the circle, you have the circumference. That is 2 pi r. So that is why we have something like this. So if you go there, I can say my I will equal H times 2 pi r. Okay? Thus the H is I over 2 pi r. That is what the magnitude